We've got an office full of high-speed computers and sophisticated drag and velocity prediction software, and have used these programs for years to predict how our sailing designs would respond. We've used them again for this project. But for added insurance, Oceanic Consulting in St. John's, Newfoundland has the most sophisticated tank test program in the world. It's where all the hottest race boat designs are tested, so they have good experience with long, light canoe body type hull shapes. Here's the new boat at moderate cruising load, going 12 knots. Compare this bow wave to what you've just seen. It's a little smaller than even Beowulf, which is what we'd expect given the improvements we've made in overall efficiency. This wake is at 12 knots. Look familiar? Let's speed up to 16 knots so we have a direct comparison with Beowulf's stern wake. The tank test and that of the video shot on board Beowulf are almost identical. This is slightly cleaner, which is what we would expect to see. What we've been trying to show you is the evolution of this species. Each new series has benefited from the experience of the previous designs. And now, in the present, we've simply moved up another rung of the evolutionary ladder. We started out talking about the heavy weather aspects of the design. There are two characteristics which stand out above all others. First is steering control. Steering control determines which tactics you can use and which you can't. And in moderate conditions, steering characteristics are a chief determinant of cruising comfort. The more speed you can maintain, the less chance there is of being caught by a storm in the first place. And if you are caught, you have more heavy weather tactical options at your disposal. We know from past experience on a numbers basis and from gut instinct based on more than 250,000 miles of open ocean sailing that the new boat will be equal to or better than Beowulf in heavy weather. But in the 21st century, we've got some incredible new design tools to verify what our experience is telling us. One of these tools is called CFD analysis. Using CFD, computational fluid dynamics, we can test different hull shapes, combinations of weight and fins at a variety of speeds, wave size, and angles to the waves. We get back an incredible array of numeric data from around the hull, in addition to these very interesting visual representations. What we've been looking at here is the hull running at 12 knots with quartering seas and significant wave heights of 8 to 10 feet. Notice the motion, or lack thereof. This is exactly what you would expect from Beowulf, broad-reaching and similar conditions. Now we're heading upwind, this time with waves of 3 to 6 feet, and the boat moving at 10 knots. There's little motion, and with our interior close to the pitch center of the boat, the motion we feel will be negligible. For our reality check, let's take a look again at that footage of Deerfoot 2 in similar conditions. Here's Sundeer on the same day in British Columbia. In this CFD strip, the new boat is facing Sea State 7. This means significant waves of 20+ feet with occasional 30 and 40 footers. The boat is slowed down to just 6 knots. It may be comforting to know that we've never encountered upwind seas of this size in our entire cruising experience. Speed up to 9 knots, bring these same waves 40 degrees off the bow, and the ride smooths out considerably. If you sail enough miles on these boats, or watch enough video, after a while you become accustomed to the comfort. It becomes second nature. But in the world of short-handed cruising sailboats, we know that we and our clients have become spoiled. To go this fast with this little motion and be this comfortable, it's almost cheating. Crossing oceans is not supposed to be this easy. There are a whole series of factors which make this possible on our sailing designs. For one, the hull shapes are balanced with heel and have favorable length to beam ratios. This helps steering control. This combination of hull shape and boat speed creates a dynamically stable system, which gets more stable the faster it goes. We've also got rig pressure to help keep the boat from rolling. On the new design, we have maintained the same type of length to beam ratios, and to provide the stability of the rig, we've added active stabilizers. These are like a pair of giant spade rudders, one on each side of the boat, hydraulically operated and controlled by a sophisticated gyro and computer. As the computer senses the boat starting to roll, the stabilizer fins generate an opposing force. We've also got a very efficient keel to help with dynamic stability, along with a pair of skegs at the stern. These protect the props from debris while cleaning up the water flow. The skegs will also help with downwind control in heavy weather. These twin rudders are enormous by powerboat standards, just right for maneuvering in tight quarters and handling the boat at slow speeds in breaking seas. Our expectation is that in moderate weather we'll have no heel and virtually no rolling. And in heavy going we'll have modest rolling but no heel, with overall a more comfortable motion than even Beowulf exhibited. When we're powering upwind, we expect to be considerably more comfortable than on Beowulf or Sundeer. Because we don't have to worry about the hull shape when heeled, we've been able to carefully carve away buoyancy that would be required in the bow and stern for stability. This makes for a knife-like bow and finer stern. This hull shape will penetrate big waves much further before starting to respond. And when the wave reaches the stern, it will find less hull on which to exert its force. The result will be a very smooth ride. That's what we've been looking at in these CFD images of the boat going upwind. While the emphasis of what we've been talking about is comfort in adverse conditions, the vast majority of our time at sea has been spent in very nice weather. Before we leave this subject, we need to discuss an aspect of heavy weather design that underlies all of our boats. I'm talking about the risk of capsize. Speed and maneuverability will go a long way towards keeping us out of trouble. But what happens if we're caught in breaking seas and we make a mistake? In this situation, the inherent design of the boat has to provide our security. Here's a stability curve for the new boat. It shows us that she will quickly right herself even from a complete capsize. Look at this simulation of the boat heeled 45 degrees after the impact of a breaking wave. What we want to happen is for the boat to skid sideways with the force of the wave. Skidding allows more time to dissipate wave energy and reduces the risk of capsize. Notice how the deck edge is barely immersed and the port side foils are out of the water. The more the boat heels, the easier it slips along with the wave. Another factor is the natural angle of the boat on the wave crest. Ideally, you want the hull to head down the wave bow first. This reduces wave impact on the aft deck where our dinghies are stored and allows the hull to assume a position that has more resistance to capsize. With our fins well aft and the forward quarter of the hull totally out of the water, there is a natural tendency to assume this ideal attitude. Let's look at the hull knocked down to 90 degrees. At this point, only the starboard stabilizer is providing resistance. The engine room air intakes are built into the aft deck breakwaters. These have downpipes which drop deep into the hull. At this angle, the air intakes are still well above the waterline. Notice how the deck hatches and offset watertight door into the saloon are still clear of the waterline. Here's what it looks like knocked down to the point of vanishing stability, 135 degrees. It's nice knowing that even in a full capsize, the boat will come back upright. The air intake downpipes into the engine room are still well above the heeled waterline. We don't dwell on capsize or even heavy weather when we're cruising. So you're probably wondering why all the emphasis on weather that's so rare. The answer has two parts. First, we want to know we've got a boat under us that will deal with anything Mother Nature dishes up. And that gives us a wide array of tools with which to take her on. Equally important is the fact that every single aspect of the design which helps in heavy weather also makes the boat more comfortable for long ocean passages.